Right, everyone, good afternoon once again. So let's begin our class. Today I want to finish off this chapter, and then Friday we'll have a review for your exam, which is on Monday. So let's first sort of recalibrate ourselves. Today is March 3rd, 2021. So we will have an exam on Monday, March 8th. So that will be our test number 2. Should be the same format as test 1. Right, there'll be a multiple choice portion and a written portion. The written portion should be open by this Friday. So multiple choice plus written. And we'll upload it to Canvas. So this Friday we'll have a review, so make sure you come to this Friday's class or make sure you watch the recording for Friday's lecture. Your quiz 2 will be due on March 8th, so make sure you upload quiz 2 on March 8th. As well as your multiple choice test, as well as your written portion of the exam. Make sure you show all your work for full credit there. And you've done the lab. Well, I think only 3 of you have done it, but there's a lab report on rates, the rates of the reaction. So upload that if you have not come to the lab. That is this Friday. So make sure you come and perform that lab and do that lab report. Homework 14 will be due on Friday. So I'll put the 10 points in. Remember, homework is just practice. And that's all I can think of. Okay, so also do those clutch prep drills. They will help you. And I'll give you some extra credit if you do everything. All the videos, all the quizzes, all the... excuse me. All the whatever they have you do. Okay? And your exam 2 on Monday is going to be on chapters 13 and 14. Bye-bye. Chapters 13 and 14. All right, so let's finish off chapter 14 in today's lecture. Any questions? Am I missing anything, you guys? I think I'm all good. All right, so. Right, so where we left off on Monday's class was talking about Lashawn's principle. So again, we're talking about an equilibrium. Okay, an equilibrium that settles. Okay, it could settle this way, more products. It could settle this way, more products, P. It could settle that way, more reactants, R. It could be the same, 50-50. In that case, your equilibrium constant is 1. Okay, so wherever it settles, that's where it will be at the end of the hour, at the end of the day, at the end of the week, at the end of the month. At the end of the year, the reaction will settle, some reactants and some products. All right. So what happens if you disturb this? Okay. Disturbing this is Lashawn's principle. Okay. So if you do something to an equilibrium, okay, it's going to bounce back. Okay, it's going to bounce back. All right, it's going to reverse whatever you did to it. All right, so if you punch me and I move back, okay, I'm not going to sit here and stand here and take it. Okay, I'm going to come back to where I was before. Okay, same thing with an equilibrium reaction. Okay, how do we compensate, or how does the reaction compensate to what you do to it? Okay, it's going to do the opposite of what you guys do to it, or what I do to it, or whatever is done to the reaction. All right. So where we left off was talking about gases. So this is a little bit confusing. Okay. A little bit confusing. So let's go over this again. So let's say, so notice here, this is an equilibrium, the back and forth arrows. So notice we have all gases. Okay, or if you have one gas or two gas, anything with a gas. Let's say we do something to this equilibrium. It's nice and settled. We're going to disturb it. We'll disturb it by increasing the pressure of the gas. Increasing the pressure. Sort of squishing the gases. So what is the opposite of increasing the pressure? Dealing with gases. The opposite is decreasing pressure. So where will the reaction shift? It will shift to the side with less pressure. Okay, which side has less pressure? The side that has the less number of moles, right? Okay. So that's how you want to do these types of problems. Okay, let's say you decrease the pressure. Okay, so instead of going like this, if they're gases, you go like this. You decrease the pressure. So I ask you guys, what is the opposite of decreasing pressure? Opposite of decrease is increase. Pressure P. So which way will the reaction shift that has more pressure? More number of moles or less number of moles? Okay, it's going to shift to the side with more number of moles. More moles, more pressure. More moles, more pressure, more collisions. Okay, more reactions. Okay, if you have more number of moles, there's more pressure. We're in this room now. Okay. If I say, class, let's meet in the closet, that's a lot of pressure. Okay. Same thing here. So Lashatier's principle, if you decrease the pressure, the reaction will counter by increasing pressure, and it will shift. The reaction will shift to the side with more number of moles. All right. These next two are a little bit tricky. Okay, what happens if we increase the volume? Well, what's the opposite of increasing volume? Decreasing volume, correct? Okay, so which way will the reaction shift that has a decreasing volume? Where it's more concentrated or less concentrated? Decreasing volume. Less concentrated. So less concentrated is that the side, Harper, with more number of moles, or the side that has less number of moles? Decreasing volume. So which way will the equilibrium go?
Less number.
Decreasing volume, does that have more moles or less moles? Are you concentrating it or diluting it?
Less number. Wait, hold on a second.
Here's my volume.
It's like the same amount in a smaller place, right? Like
Same amount in a smaller place. Okay, class, I'm going to teach in the closet. Okay. So, what will we do? How will you react? You're going to go and move out, right? Okay. So you're going to go to the side with the most number of moles. All right. Decreasing volume. So the reaction will shift to the side with more number of moles. Okay. You're going to go where there's more. You're going to go out. Probably the example doesn't make sense, but let me see if I can explain it better. So Robert, if we increase the volume, okay, we're all happy. We're increasing the volume. Okay. What will the reaction do?
You get less number.
It will decrease the volume. Okay, U increases the volume. What will the equilibrium do? Do the opposite, decrease the volume. So which side has decreased volume? Which side has decreased volume? More moles or less moles?
More moles.
Yeah, more moles. So it's going to increase to the side. It will shift to the side with the more number of moles, more concentrated. Say more concentrated. Does that make sense, Robert and everybody?
When it says, like on the notes, doesn't it say decreased volume, and then it says with moles and fewer moles?
Yeah, that's what I was going.
That's what I'm confused about. Because when it says increased volume, it says side with less volume.
Yeah, that's more concentrated. The side that's more concentrated has a decreased volume. Which is more concentrated, this or this? So it's going to go to the side where it's this. This side has more number of moles. Right?
Yeah, that, because like you said, decreased volume is side with more number of moles, so then that says decreased volume, side with fewer numbers.
Now we're still on the blue arrow. We're increasing the volume. How will the equilibrium react? Okay. If you decrease, forget about this point here. Let's focus on this. If we increase the volume, okay, what will the reaction do? What's the opposite of increasing the volume? Decreasing volume. So which side has a decreased volume? It's the side that's more concentrated. All right. And now let's go to the last one, where you decrease the volume. Okay, if you decrease the volume, what's the opposite of decreased volume? Increased volume. All right, do you see this? Okay, so you decrease the volume. How will the reaction behave? Opposite. So what's the opposite of decreasing volume? Increasing volume. So which side has increased volume? More concentrated or less concentrated? Less concentrated. So which side is less concentrated? More number of moles or less number of moles? Less. Does that make sense?
I just don't get it.
Huh?
I just don't get it.
All right, let me see if I can explain this again. Where are you lost?
I'm just confused because you're saying decreased volume.
This one, right?
Right.
Okay.
And then it says shift in the equilibrium. And
Right.
Doesn't that say fewer? And then you're saying it says more.
Yes, so if you decrease the volume, you decrease the volume of a reaction with gases. What's the opposite of decreasing volume? Because the reaction is going to do the opposite, right? So you decrease the volume, or whomever decreases the volume. Okay, so the reaction will shift to the side that has increased volume, right? Does that make sense? Right? With me so far? So we have a reaction with gases. You decrease the volume. Where will the reaction go? To more volume or less volume? Increased volume, right? So which side of the reaction has increased volume? Which side of the reaction has increased volume? Is it the side we're dealing with gases? Which side of the reaction has an increased volume? Is it the side that has a more number of moles, or is it the side that has less number of moles? Less number of moles. Okay, if you increase the volume, okay, you're getting more dilute. Okay, so this reaction will shift to the side that has a less number of moles. We're talking about gases. Where your confusion point is, you don't realize that these are gases you're talking about. Okay, gases. So here we have, if we're all gas molecules, okay, we're in a room, okay, we have a certain pressure. Okay, we all exert a certain pressure, we all bounce around and stuff. Okay, we take ourselves and move to the closet. Okay, will we have more pressure or less pressure? More pressure there. Okay, less volume, more pressure. Okay. Here, more volume, less pressure. Remember, pressure has to do with the collision frequency. We'll have a practice problem at the end, so we can see if that will help solve your problem. But for now, let's move on and we'll do the practice problem here. All right, so obviously this is a little bit confusing because you have to think counter. Once again, let me explain. If you decrease the volume, the reaction will shift to the side that has more volume. The side that has more volume is the side that's less concentrated. The side that is less concentrated is the side of the reaction that has a less number of moles. Okay? So this is the opposite. The reaction will do the opposite of whatever you do to it. All right? All right, so that is gases. Okay, what about heat? Okay, and Le Chatelier's principle. All right, so before I talk about this, I wanted to tell you, you guys should discriminate between an exothermic and an endothermic reaction. So if I have A plus B goes to C plus D, if my delta H is minus, okay, this is called enthalpy. If it's a minus sign, negative 300 joules, negative whatever, negative number, we call that an exothermic reaction. Okay, so if it's an exothermic reaction, this liberates heat. Okay, the opposite of this is an endothermic reaction, which requires heat. So let me write the same thing here. But my delta H, okay, let's remember this is called enthalpy. More specifically, change in enthalpy. Let me turn off the lights. Change in enthalpy. So if it's a positive value, we call that an endothermic reaction. An endothermic reaction requires heat. You need to put some energy in to make the thing go. So this is a reaction that requires heat. So just remember, if your delta H on the exam or the quiz or wherever, if your delta H is negative, we call that an exothermic reaction. Exo means outside. And usually the enthalpy will have a negative value. And the opposite, if this reaction requires heat, it's an endo. Endo means taking in, endosperm or endoderm inside. So it's taking in heat. So that's an endothermic reaction. This thermodynamic parameter, change in enthalpy, will have a positive value. And I'm going to move on here to our last couple of pages here. All right, Le Chatelier's principle and catalysts. Okay, so do we remember what a catalyst does? Very good. It speeds up the reaction. It lowers the activation energy and it speeds up the reaction. Okay. Okay, it lowers the activation energy. That's called E sub A. Oh, I'm sorry. Speeds up the reaction, lowers E sub A. So what do you think it's going to do to K equilibrium constant, and what do you think it will do to lowercase k rate constant? So this is important and confusing. Remember, we had two K's. One was lowercase k, the other was big K, equilibrium constant. So what do you think it will do to equilibrium constant? Capital K, a catalyst. Okay. It's not going to do anything. Okay, so this remains unchanged. But what will it do to lowercase k, rate constant? Well, if something speeds up the reaction, you guys, Adriana said it. Okay, a catalyst speeds up the reaction, and she's right. So what do you think is going to happen to rate constant k, lowercase k? Higher or lower? Higher. Okay, so you see the catalyst, very correct. The catalyst, try saying this real fast. The catalyst will increase rate constant, but it will leave the equilibrium unchanged. Okay, just arrives at the equilibrium faster, right? It just arrives at the equilibrium faster. Well, if it arrives at its equilibrium faster, it means the rate constant for that reaction, that equilibrium, is going to be higher. Rate constant, miles per hour, except we're talking about reactions. So it'll go faster, miles per hour, even though it's not really miles per hour. Right? So those are the things we should know with regards to Le Chatellier's principle and catalysts. All right, Le Chatellier's principle and catalyst, equilibrium constant. By the way, this is equilibrium constant and rate constant. Equilibrium constant, nothing happens. Rate constant, because as Adriana said, speeds up the reaction, so obviously rate constant is going to be higher. All right, let me talk a little bit about Le Chatellier's principle and heat one more time. Let's go back to this. All right, remember, A plus B is in an equilibrium with C plus D. Okay, I tell you the reaction is exothermic. Okay, so if I tell you the reaction is exothermic, that means two things. Number one, your delta H is negative. Okay, but what also does that mean? It means we liberate heat, energy. We liberate energy in the form of heat. Okay, so now you guys don't get confused. What happens if I raise the temperature of this reaction? If I raise the temperature of an exothermic reaction? Okay, it's an exothermic reaction. Which way will the equilibrium shift? If I raise the temperature, what am I adding? Heat. Okay, so if I'm adding heat, what will the equilibrium reaction do? Remember, it does the opposite. So what will it do? It will go to the side that has less heat, right? So which side has less heat? The reactant side or the product side? Reactants. This reaction will shift to the left. Okay, remember, it's going to do the opposite of what we did to it. Very good. So obviously, Elena, if we do the opposite, if we lower the temperature, which way will the reaction shift? If I lower the temperature, what am I doing? I am removing this heat. If I'm removing heat, which way will the reaction go? It will go to the side that has more heat. Which is the side that has more heat? The right, the product side. So the reaction is going to shift to the right, the product side. All right, let's do one more. We'll do this now for an endothermic reaction. Okay, there are two things I want you to know for an endothermic reaction. Number one, the delta H change in enthalpy will be positive, but an endothermic reaction is going to require heat. Okay. All right, let's do our same situation here. We will raise the temperature, but this time we will raise the temperature of an endothermic reaction. Okay, if we raise the temperature, what are we adding? Heat. Okay, if we're adding heat, what will the reaction do, Connor?
Shift to the right.
It's going to shift to the right to remove the heat that we caused by raising the temperature. Shift to the right. Very correct. And that's the reactant side. Finally, for an endothermic reaction, what happens if we lower the temperature? Okay, lowering the temperature is removing heat. Okay, if we lower the temperature, bless you, get that heat away, which way will the reaction shift? To the side to regenerate the heat or the side that has less heat? Remember, lowering the temperature, you're removing heat. So which way will the reaction shift? To the left, this is the product side. It's a crucial mistake I made, right? Okay, raise temperature for an endothermic reaction, it's going to shift this way. Okay. If I lower temperature for an endothermic reaction, lowering the temperature removes the heat, so the reaction will shift that way towards the left. Does this make sense? Okay. I'm looking for nods. Okay, I see nods. Okay, it's going to shift left towards the reactant side. Remember, it does the opposite. Opposite. All right, so here are the two situations there. Lashatte's principle for an exothermic reaction, and here an endothermic reaction. All right, let's do a problem here. Maybe that could resolve your doubts. Adriana and others. Let's see. This is our last problem in Chapter 14, and this will end the material for the exam. All right, consider the equilibrium. 3O2 gas is at an equilibrium. Okay, how do I know it's at an equilibrium? Okay, it goes back and forth. Okay, those back and forth arrows, okay? Like a snap of your fingers, automatically think to yourself, this is equilibrium. Okay, back and forth, so it has to settle. 3O2 is at an equilibrium with 2O3. Everyone see that? 2O3. Okay. And the delta H for this reaction is 284 kilojoules per mole. The delta H for this reaction is 284 kilojoules per mole. All right. Immediately, you should see this value and ask yourself the question: is it positive or negative?
Positive.
It's positive. So is that endothermic or exothermic? Endothermic. So does this reaction, based on this value, give off heat or take in heat? It requires heat is correct. Okay, so I'm going to amend this reaction by saying heat plus 3O2 gas is at an equilibrium with 2O3 gas. By virtue of this being an endothermic reaction. All right, Robert and Adriana. Oh. Okay, I want you guys to look at A. All right, what would be the effect of the equilibrium if we increase the pressure? Okay, Robert, I'll pick on you. Okay, if we increase the pressure, what is the opposite of increasing pressure? I'm not asking you to answer this. I'm just going to try to lead you to the answer, hopefully.
Oh, I was going to say decrease volume.
Okay, increasing the pressure is the same thing as decreasing the volume. Do you agree that these are the same? Okay, decreasing the volume. Let's go to the closet versus let's go here in room H245. Right, so these two are the same. Do you agree with me, Robert? Okay. All right, so what's the opposite of increasing the pressure?
The opposite of increasing pressure.
Right, the opposite of increasing the pressure.
Oh, we just said decrease in volume.
That's the same thing, right?
So you would
Well,
increase the volume.
Oh, okay. Increase the volume on the other side.
Yes, so the opposite is increasing the volume or decreasing the pressure, right? Correct? Are we all in agreement? Yeah. Okay, the opposite of this, increasing the pressure, what's the opposite of increase? Decrease.
So that's the answer, or is that just...
No, I'm just
Oh, okay.
leading you to the answer. What's the opposite of decreasing the volume? Increasing the volume. So the opposite here is decreasing pressure, increasing volume. Okay, are we all with me so far? Okay. Okay, now I want you guys to tell me the answer. Which way will the reaction shift? Okay, it's going to shift to the side that has less pressure and more volume, which is the same thing. So which side is that? Reactant side or product side?
Product side.
Everyone, I cannot speak for the life of me today. I must be going through puberty again. I don't know what's going on. You're right, okay? The side that has the increased volume and the side that has decreased pressure is going to be the product side, okay? You see 2 exerts less pressure than 3. 2 moles of O3 gas exerts less pressure than 3 moles of O2 gas. 2 moles of O3 gas will take up more volume than 3 moles. Okay, 3 moles is a little more concentrated. 2 moles, less concentrated. So the correct answer here is you guys are correct. It goes to the product side. I'll pause here. Okay, does this make sense for you guys, Robert and Adriana? Okay. My wife calls me stupid every day, so I must feel I'm also stupid then. Are you okay?
Yeah.
We can talk also on Zoom or whatever, because this is weird, this is difficult. You have to think counter. Robert, what do you think?
Just overthinking it before. Now it makes sense.
Definitely.
Like in my head, I imagine like a hydraulic shock. So like when it goes down, it's decreasing the volume.
Yes.
Which is increasing the pressure.
Correct.
So like yeah, that's.
So that makes sense. So you should.
So, all right. So what will what will the reaction do?
It'll be on this, yeah.
It's going to increase the volume and decrease the pressure. Okay. Like the hydraulic pump, you said? Hydraulic shock, okay? You push down, the reaction will push up. So here, the reaction is counterbalancing whatever is done to it. The issue is that you're dealing with gases. Gases exert a pressure.
But there's gases in like shocks. So
Right.
that's
Yeah. So think of this as like a shock, hydraulic shock.
the way I had to like try to make myself understand it.
And once it's applied, it makes more sense.
Yeah. I think the confusion is that these are gases. Gases are a little bit opposite. All right, how about adding O2 to the system? Okay, what's the opposite of adding O2?
Taking it away.
Taking it away. Which side takes away O2? Yes, the product side takes away O2. Okay, this will not shift. So you add O2, the reaction will not shift to make more O2. Okay, it will shift to remove the O2, and Connor's correct. This is the product side. Okay, the reaction will shift to the product side. All right, decreasing temperature. What will that do to this reaction? Okay, remember it's endothermic now because it's positive delta H. Reactant side is the right answer. See, if you decrease the temperature, you remove heat. Right? You're decreasing the temperature, you're removing this guy. The reaction will go to generate more heat, so it's the reactant side. Okay, very good. Right? By virtue of this being an endothermic reaction, this is shifting to the reactant side. Okay, what happens if we add a catalyst? Left or right? Nothing. Okay, it just achieves this faster. Okay. Okay. Catalyst really, you can't tell whether it's going to go this way or that way because a catalyst. The only thing you know is that this is just going to happen a little bit more faster, a little bit more quicker. Okay. All right. So that is chapter 14. We are done. We have 15 more minutes left. Do you want me to move on to 15? A little bit of a teaser, or? All right. By the way, I printed out 2 extra copies. Does anybody want one?
Always. Thank you.
Anyone else? One more? Let me take 5 more minutes. Let me take 5 minutes here. I know a lot of you want to just focus on 13 and 14, but let me just tell you a little bit about chapter 15. It's about acids and bases. Okay. Okay, acid-base chemistry. All right, so those are the only thing I'm going to tell you now, and then I'll let you guys go. So an acid is going to have an H by it. Okay, acid will have an H by it. We call that H a proton. And something else, okay, we'll call that A acid. So this is what an acid does. Okay, more specifically, this is what a Brunstad acid does. Okay, an acid will react with water. Okay, here's that equilibrium again. Acids are going to do this. They're going to give a proton. They give a proton, and they're going to give you a substance known as this H3O plus, and this A becomes A minus. All of this is happening in the solvent of water. Okay, I want to tell you one thing about this H3O plus. This H3O plus, the way I'm going to teach you guys this H3O plus is going to be the same thing. Okay, it means the same thing as H plus. Okay, this H3O plus is the hydroammonium ion. But I'm also going to call it proton. Okay. So if I use H plus, I mean H3O plus. If I use H3O plus, I mean H plus. Okay, so this is very important. These, the way I'm going to teach this to you is the same thing, interchangeable and synonymous. This is called an acid, more specifically a Brunstad acid. I'd like for you guys to know this equation. Okay, A is any acid. There's thousands of acids. Okay, we'll get into specifics later on in the chapter. Okay. And now let me tell you about a base. Let me rewrite this first of all. And I'm only going to do a little bit of a couple more minutes, so just bear with me. There's that H. So acids are going to give away protons. Okay, give away protons. Some do it better than others. Some do it better than others. Okay, for example, hydrochloric acid. Okay, why do you think it burns? Okay, because it gives away protons and messes up your skin. Okay, acetic acid, vinegar. Why do you think it's not as bad? Spill some. It's okay. It's not as strong as an acid. All right, that was an acid. Let me tell you what a base is. So I'm going to take this A minus. See, this is a base. Okay, water is always a liquid. Here's a base. Okay, bases are going to take protons. See, acids give away, bases take. Bases abstract. Okay, they abstract, they take. Okay, if Elena over here has a proton and I am a strong base, I'm going to grab it from her like anything because I'm a strong base. Okay? So bases are going to take protons, H+, and they're going to give you hydroxide ion and a little bit of that acid back. Okay. So this is what we call a base. I want you guys to know this reaction. Okay. There's thousands and thousands of bases. There's thousands and thousands of acids. Okay. They're all going to do this equation. Some of them better than others. Okay. Some of them better than others. We're going to call this reaction up above Ka. We're going to call this reaction down below Kb. Equilibrium constant Ka. Just give me 2 more minutes. Products over reactants. That's the equilibrium constant for this acid. Okay, why did I not put water in there? Okay, for next Monday's exam, no liquids, no solids. Okay, I'm going to do the same thing for Kb. Products over reactants. I want you guys to memorize the generic. Okay, we'll get into specific chemicals later. both of these are equilibriums. All right, so here we have the Ka for this acid. Here we have the Kb for this base. Want to also tell you guys that acids give rise to H3O+. Bases give rise to OH-. I want you guys to know those equations. Finally, I'm going to add these two. I'm going to add these two reactions, and this is the last bit here. If I add these two reactions, I multiply the equilibrium constants. Another thing happens. A- cancels out with the A-. The HA cancels out with the HA. And look what happens when I add these two reactions for the acid and for the base. This is amazing. Okay, water plus water is 2H2O. Is in at an equilibrium with H3O plus OH minus. Remember, H3O plus and proton is the same thing. Okay, the way I'm going to teach it. When we add two reactions, we multiply the equilibrium constants, remember? Okay, that's on the exam on next Monday. When we add two reactions, we multiply the equilibrium constant. So this will be Ka times Kb. We will call this Kw. Ka times Kb is equal to Kw. Another K. Told you there's going to be lots of Ks, equilibrium constant Ks. By the way, this Kw is products over reactants. We don't add the water because water is a liquid. All right. There's many more things to say about this. From here, I can derive for you guys pH. How many of you know what pH is or heard of it? POH and all sorts of things. But we will wait till next week to do that. All right. So make sure you remember this. Make sure you remember this. This is an acid. This is a base. Also, there's going to be acids that are strong, and then there's going to be acids that are weak. There are going to be bases that are strong, bases that are weak. All right, I'm done talking. Have a good day.